In this video, I wanted to talk more about the relationship between numerical and graphical ways of determining limits, and really, what are the different ways of finding limits actually, I listed a few in one of the slides that's upcoming, and I wanted to say, in this class, what we're going to focusing on, like which method should we focus on. But I like to think of really there's three main ways of determining limits in terms of figuring them out. Basically, there's the numerical and the graphical approach, which I wanted to get back to in this video. There's also an algebraic approach of finding limits, which we're going to also talk about in the upcoming sections. Using a few different tactics. Direct substitution is the easiest, but doesn't work a lot of the time. Whereas sometimes we can do an algebraic manipulation, meaning just use some algebra, such as canceling, simplifying, factoring, whatnot, to actually then be able to perform a direct substitution. Or sometimes we can even use mathematical theorems to do it as well. And then the fourth method that I have listed here is something that we're not going to do in this particular class, but limits do have a very precise way of being defined mathematically, because a lot of, as we talk about limits in these videos, it can seem kind of like not necessarily guessing, but we're not really necessarily sure that it makes sense. We're kind of doing our best idea of estimating or determining what the limit is, especially using a graphical and numerical approach. We're not solving it, we're not proving it, we're just sort of finding it via anecdotal evidence. So let's get back to an example of, let's start with the numerical approach. And basically, the idea here is plug in numbers and see what happens. It's kind of like in the last video when I was describing the limit as the limit of 1 over x. As x heads to infinity, we had that y headed to 0, because basically if I plug in plugging into, I'll just go back to that slide, like plugging in larger and larger values resulted in a smaller and smaller fraction in that particular case. And limits are going to be different for whatever equation or function that you're working with. So let's start with a new function. Let's look at a quadratic function, f of x is equal to x squared minus x plus 2. And just kind of doing a quick recap, remember that when a polynomial is degree 2, x squared, we call it quadratic, and it often takes the shape of, well, it always takes the shape of a parabola, assuming it is a quadratic function. You can find things such as the vertex, axis symmetry, so forth, all that algebra. A lot of that we don't need to worry about. But, you know, when finding limits, we're trying to understand more about that particular function. And let's say we wanted to know what the limit of the function was as x approaches 2, or again, trying to find the behavior as we have it on the right-hand side. So over here we have it listed as x approaches 2. And like, again, if we were going to do a graphical approach, we could just graph it and look at what happens. And with most functions, especially ones which are continuous, as all polynomials are always continuous functions, just meaning that they don't have weirdness. We'll talk about more about what that means soon. We have y approaches 4. And like if we're looking at the graph, we could see, well, here is x is equal to 2. We have our parabola, which is f of x graphed in blue. If we look at the left-hand side as x approaches 2 from the left, it's headed towards this particular point, 4. And it's going to get closer and closer and closer to that. And as x approaches 2 from the right-hand side, it's also approaching 4. From both directions, it's headed towards that point. And what you might be thinking to yourself is, well, if I want to know what happens as x approaches 2, why don't I just plug into the function, right? Because I know what's going to happen. That's going to be f of 2. It's going to give me the y value at that particular location. I would get 2 squared minus 2 plus 2, which is, of course, 4 minus 2 plus 2 is 4. And so f of 2 is 4. That gives me the correlation of the function. Like in this particular case, the limit or the approaching notation means nothing different than that. So in a lot of senses, this doesn't, it's kind of the same thing we're familiar with in math. It tells us the correlation between x and y. But the reason I started with that last example, which was a little more complicated, is because a lot of times that correlation is not as simple. Like especially when it comes to undefined things, such as, well, what's 1 divided by infinity? What's 1 divided by 0? Certain times in math, it's not simple. That's usually when a limit we need to determine the limit instead. And when it comes to the derivative, a fundamental term to calculus, limits are involved in that process. So again, that would be a graphical approach, kind of method number 2. A numerical approach is instead looking at the numbers. Instead of plugging in specifically 2 as I did above and figuring out what comes of it, we would want to check what happens close by. Because really, as x approaches 2, that doesn't mean what happens at 2. That means what's happening as I get closer and closer and closer from, well, technically both sides. But we could look at what's happening from the left-hand side as I did up here, and then look at what's happening from the right-hand side as well instead. And basically, let me move my head again because I'm in the way. Like, if you're wondering, well, where do I begin? Like, notice how you could always begin like 1 unit to the left. So like if you start at 1, you could see what happens. Well, if I plug in 1 into f of x, I would have 1 minus 1 plus 2. That would give me 2. But, you know, moving just 1 unit away, that's often not close enough. Ideally, we'd want to get as close as we possibly can in order to try to understand the limit. Because, you know, the way that we determine what's happening with the limit is by getting closer and closer and closer, really getting as close as we possibly can before we want to pull our hair out from having to do so much math. And using a calculator can often be quite helpful here, or a table of values, because then you don't have to actually do the math yourself. But here I've provided a bunch of values just to help illustrate this point. And what I can see is, well, what happens as x approaches 2 from the left. So we would call this a left-hand limit, or from the left-hand side, because I'm starting to the left of 2 and getting closer and closer and closer to 2 as I progress through this table. So if I get to 1.5, or right in between, it's going to give me 2.75. If I go to 1.8, I'm going to be right about here on the graph, and I'd be at 3.44. 1.9, 3.7. And what we can kind of see through this progression is, well, as I plug in numbers that are closer and closer and closer to 2, I could try to see, well, what's happening. And if you pause for a second to think, well, what do we think is happening? What is happening to the value of the function as x approaches 2? You can see it's getting very, very close to 4. So theoretically, we could say, well, it appears as though it's getting closer and closer to 4. Again, this would be called a numerical approach to determining a limit. Notice this is not an exact process. This is kind of a guesswork where when I figured out that f of x or that f of 2 above was equal to 4, that would be called direct substitution, because I'm literally plugging it in, which is a method of doing it. But if I look at it from the left-hand side, it's approaching 4. That would be my guess, is because it's getting very, very close to 4. And if you're not really sure, is this going to get closer and closer to 4, you could just keep getting closer and closer. Like you could go 1.99999, 1.9999999, and eventually get to the point where, okay, this is headed towards 4. Again, from the left. Now, also with limits, you'd never want to just check one direction, because we refer to this as the left-handed limit, whereas the right-handed limit, we want to check to make sure it's working in the same direction. And this is, based on a definition in a slide that's coming up in a second. But another key idea with limits is you want both directions to head to the same point in order for the limit to exist. The limit does not exist if there's contrary points, if it's pointed contrary different locations, just because the basic idea of a limit. But if I wanted to check from the right-hand side, I'd want, again, examining the same limit, what happens as x heads to 2? From the right-hand side, you could start 1 unit to the right of 2, say at 3. And again, there's no right way to do a numerical limit. It's just starting a little bit to the right gives you a sense of what's happening. And if I go to 3 up here, and I plug 3 into this function, I would have 3 squared is 9, minus 3 is 6, plus 2 is 8. So f of 3 is 8. And that's not 4, obviously. But I'd want to get closer and closer to 2 to see what's happening from the right-hand side. And if I check the table of values, what's happening as I get closer and closer to 2 from the right-hand side, well, 2.5 would yield me 5.75. 2.2 would yield 4.64, and so on. Basically, they're all points along that continuous graph that form the shape of the parabola of the original f of x. And mathematically speaking, those numbers are going to, again, you could plug these into a calculator to do these yourself if you were trying to figure them out. But if I plug in, say, 2.01, a good place to start is moving just very slightly to the right and very slightly to the left of 2 to see, do they match up? Are they pretty close? In this case, 4.03, I can see that this is also getting closer and closer to 4. And at the end of the day, what we conclude, if we're looking at these numbers, is that as x approaches 2, both from the left-hand side and the right-hand side, the value of y, or the value of f of x, the function, is heading towards 4. And in summation, we'd write this using limit notation in the following way. So on the last slide, I didn't use limit notation yet. I was just using the arrows, the approaching notation for end behavior. But limit notation, I'll go ahead and talk about what this means right now. We refer to this as the limit as x approaches 2 of f of x is equal to 4. And this is the way you'll see limits in your homework a lot. And a limit is just another way of saying, well, what's happening as there's always going to be a little subscript beneath the limit, which should describe where. Because a limit doesn't really mean much. It's not like a direct mathematical function. Well, it does mean something, and I wanted to talk about the abstract idea of a limit as opposed to the precise definition of a limit. But it essentially means what I've been describing. The limit as x approaches 2 means what's happening as I'm getting closer and closer to 2. And basically what always comes after the limit is kind of like, well, what am I taking the limit of? It's sort of like a operation upon a function. Typically in calculus, we do limits of functions. In this case, it's describing this quadratic function x squared minus x plus 2. And like another way that you could write this analogously would be limit as x approaches 2 of the function. Often you might use a parenthesis and put it within here, like put it within parentheses like this. Basically, as a mathematical, it's sort of like an algebraic expression, like 3x plus 4. The limit means I'm actually doing something to it. It's sort of like evaluating it. In this case, it ends up being equal to 4 because that's what we get as our outcome. In both cases, from the left-hand side and from the right-hand side, it's heading to 4. So that would be my conclusion as what the limit is from the graphical. And again, the table would be from a numerical standpoint. From looking at the graph, it looks like it's headed to the same point, meaning that would be the value of the limit. And that's what happens on the other side of the equal sign. The limit of something is equal to what it's headed towards at the end of the day, which just so happens to be equal to the evaluation 4 in the same case, where a lot of the time, under most normal circumstances, this will be the outcome of limits. In the homework, we're often focused on stranger behavior and instead of the easier to determine limits. Because this one I would say would be easy just because it's just equal to f of 2, which is 4. So let's now look at the definition, the intuitive definition of a limit. It says, suppose f of x is defined when x is near the number a, meaning that we're allowed to plug into it and it's working as in the previous examples. And notice it doesn't have to be defined at a for this to work. It says, then we write limit as x approaches a of f of x equals L. And this is how we say it, as I have been, but it's nice to practice this in your head as you're reading limits. The limit of f of x as x approaches a, and again, it's of f of x because that's what the limit's being taken of. And again, you can say that in any order. The limit as x approaches a of f of x, or as it's written, equals L. And having it being equal to L just implies that there is an existing limit, a value that this function is heading towards. Now, limits we sometimes say are equal to infinity, as I was sort of precursoring in the other video. Sometimes it could be equal to 4, it could be equal to 2, and sometimes limits do not exist. That's another case that could happen. And it says, we can define it this way if we can make the values of f of x arbitrarily close to L by restricting x sufficiently close to a but not equal to a. And this is kind of a key thing with the limit. You're technically not ever plugging in a. That's not part of the limit. The limit is looking at nearby, not that specific point. But in the previous example, it sort of seemed like plugging into would just give you the proper outcome. But it's sort of cheating the limit, if you see what I mean. Because really, finding the limit involves examining all of these numbers. As I get sufficiently close to 2, and again, the question is, what does sufficiently close really mean? But it's kind of just like get as close as you can, or as close as you need to really determine what's happening to the limit. And as we'd say that it's getting sufficiently close to 4 as x gets sufficiently close to 2. And that's really reflecting the definition. This isn't the definition of a limit, but it's the intuitive definition. It's not like a formalized definition. The formalized definition is a little bit more rigorous and something that we're not gonna really bother too closely with. So anyways, let's wrap up this video. It's getting a bit long, but we're gonna be looking at it in a couple different lights. And what I recommend you do when you're working on your homework is try to think about it in multiple different perspectives. Try to think about it from the number crunching method. Try to think about it from looking at a graph. And as we progress, algebraically speaking, there are tricks to make this a lot easier. There's general principles so that we don't have to do as much thinking in every single case.